A few videos ago, I dropped this word on you guys, resistance, and then I didn't define it much beyond it's the way that a material will resist current. And now I want to think about what's involved with resistance, what variables go into determining something's resistance. So let's have here some wire. And think about the question, what variables might affect the ability of electrons to move through the wire? So let's throw an electron in there and say that the electron wants to move that way because of some potential. So what variables might affect the ability of electrons to flow? Well, I already said in that video that the material itself will determine how readily some electrons will flow. So that's our easy one. Type of material. And the way that we'll speak about this is with resistivity. So resistivity is part of resistance, and the symbol that we use is this Greek letter rho. So the more resistivity a material has, the harder it is for the electron to flow. So that makes sense. We'll use copper for our wire. Next thing, maybe the length of the wire itself. So if I have a wire that's this long versus a wire that's, say, that long, this wire will take longer for electrons to flow. It'll take longer for the electron to reach its end. To reach the end. So, writing this in proportion, the resistance is what we're solving for here. Resistance is in R. It's proportional to the length. As the length of the wire goes up, so does the resistance. And, well, what else could we think about? Oh, what if we made this wire thicker? Or what if we increased the cross-sectional area? So instead of this wire, maybe we looked at something like that wire with the same amount of length. So this is A2, this is A1, and we'll say A2 is greater than A1. Well, with the greater area, there's more space for electrons to flow through from this point to that point. So this will allow greater electron flow. So a relationship between resistance and area looks like this. It's proportional to the inverse. As the area goes up, resistance goes down. So, let's put it all together into one handy equation about resistance. Well, we have the type of material, we have the length, and we have the cross-sectional area. It should make sense that the resistance here, I didn't write it out, but it should make sense that these two are proportional as the resistivity goes up. As we get something like rubber, its resistivity is a larger value, there's more resistance. So our equation then looks like this. Resistance is equal to the resistivity value for the material times the length over the area. This is measured in meters. This is measured in meters squared, an area. This is measured in ohms. In resistivity, ohm meter. So looking at a few materials, let's look at copper. It's got a resistance of 1.68 times 10 to the negative 8th ohm meters. This is not resistance, I'm sorry. This is resistivity. Because overall resistance would depend on the length of wire that I cut in the cross-sectional area of that wire. And let's also look at tungsten, which has 5.6 times 10 to the negative 8th ohm meters. So copper has a lower resistivity, meaning for any given length and area, we'd be able to get electrons to flow through copper at a greater rate than through tungsten. Okay, see you guys next video.